All right, welcome back, everyone. Ready for another deep dive. Today, we're tackling a Google research paper that's causing a stir in the NLP world. You know, natural language processing, how computers wrap their silicon brains around human language.
Definitely a hot topic.
It is. Now, anyone who's been following NLP has probably heard of the attention mechanism, kind of a big deal in the field, right?
Absolutely. Revolutionized how we build models that understand text. It's like, imagine you're reading a sentence. Your attention naturally goes to the key words, the ones that carry the most meaning. Attention mechanisms try to mimic that.
Right, focusing on the important bits. But this paper we're looking at, FNet, mixing tokens with Fourier transforms, well, it throws a bit of a curveball. It asks, what if you ditch this complex attention thing and go with something much simpler?
Simpler and perhaps surprisingly pretty effective. They're using the Fourier transform, that mathematical tool that's been a workhorse in signal processing forever.
Okay, full disclosure, when I first saw Fourier transform, I got a little flashback to high school math class, not gonna lie, but the way they use it here is really clever.
I promise, no pop quizzes. Think of it like this. Imagine a piece of music with all these different instruments playing together. Violins, cellos, flutes, a whole orchestra. The Fourier transform lets you separate out each instrument, analyze its unique frequencies.
So instead of zeroing in on specific words like attention does, FNet uses this Fourier transform to blend all the words in a sentence together.
Exactly. It breaks the sentence down into its fundamental frequencies, creates a representation that captures how those words relate, but in a totally different way.
So instead of listening to individual instruments, FNet is taking in the whole orchestra of language at once.
That's a great way to put it. And the crazy part is, even without that focused attention on each word, the model still manages to grasp the overall meaning, the context of the sentence. It's like seeing the forest for the trees.
Okay, color me intrigued. But does this radical approach actually work? How does it stack up against those traditional attention-based models that everyone's been using?
Well, they put FNet through its paces on GLUE, a standard NLP benchmark, bunch of different language tasks, all bundled together. The results were pretty eye-opening.
Don't leave us hanging. Spill the beans.
All right. FNet achieved 92% of the accuracy of a popular transformer model called BERT. And BERT, as you might know, leans heavily on that attention mechanism.
Whoa, so almost as good as BERT, but using a much simpler method. There's got to be a catch, right? Nothing's free in the world of computation.
You're sharp. The trade-off here is speed and efficiency. FNet is way faster to train. On GPUs, it was a whopping 80% faster than BERT. Even on those specialized TPUs, it was still 70% faster.
Okay, that's a serious difference. Researchers could experiment with bigger data sets, more complex models, all while saving a ton of time and computing power.
You got it. And that opens up a whole world of possibilities for pushing the limits of what we can do with NLP.
Okay, now I got to ask for a bit more detail here. You mentioned FNet uses this Fourier transform to mix up the words in a sentence. Can we break that down a little more? How does that actually work?
Sure. So you've got each word in a sentence. Each one gets represented by a vector, basically a list of numbers that capture the word's meaning.
Okay, so each word has its own numerical fingerprint.
Exactly. Now, what FNet does is apply this Fourier transform to those word vectors along what we call the sequence dimension, meaning it mixes information from all the words in the sentence based on their position.
Kind of like shuffling a deck of cards, but instead of cards, we're shuffling these word vectors.
Nice analogy. And this shuffling is what allows the model to see the relationships between words, how their order in the sentence impacts the meaning.
But hold on, if it's just mixing things up, how does it actually understand what's being said? It seems a bit chaotic.
Ah, good point. It's not just about the shuffling. The Fourier transform also gets applied along another dimension, what we call the hidden dimension. This is where all the subtle nuances and features of each word live.
So it's not just about the order of the words, it's also digging into the deeper layers of their meaning.
Precisely. And here's the thing about the Fourier transform. By its very nature, it doesn't lose information. It mixes things up, but all the original data is still there.
Pretty neat trick. So by applying this transform in two different ways, FNet captures both the order of words and the finer points of their meaning.
You got it. And that, in a nutshell, is how FNet replaces this whole intricate attention mechanism with a much simpler, more efficient math operation.
Okay, this is fascinating stuff. But I gotta ask, if this approach is so simple and effective, why haven't we been using it all along? What's the downside here?
Ah, the eternal question. Remember, this is still early research. While FNet shows a lot of promise, there are some potential drawbacks to consider.
Like what? What are we missing out on by taking this simpler route?
Well, one thing is, while FNet is great at seeing the big picture, the global relationships between words, it might not be as good at focusing on very specific, subtle interactions between individual words.
So back to our analogy, it sees the whole forest but maybe misses some of the details on individual trees.
Exactly. There might be certain NLP tasks, like figuring out the sentiment of a text or answering very specific questions, where that laser focus of attention is crucial for getting the right answer. In those cases, a traditional transformer might still outperform FNet.
So FNet isn't a magic bullet, more like a new tool in the NLP toolbox. Each tool has its strengths and weaknesses.
Absolutely. It's an exciting new direction, opens up a lot of possibilities. A great example of how thinking outside the box can lead to real breakthroughs.
Speaking of new directions, I'm curious about how FNet handles those really long stretches of text. We know traditional transformers can really struggle with things like entire documents or long conversations. How does FNet do in that arena?
Now that's where things get really interesting. They actually put FNet to the test on something called the Long Range Arena, or LRA. It's a benchmark designed to really push these NLP models, see how they deal with those extended chunks of text. Think like analyzing a whole research paper or a legal document tasks that really need that long-range understanding.
So, like a marathon for NLP models, testing their endurance for those language challenges that just keep going.
You got it. And in this marathon, FNet held its own, even against those highly tuned, efficient transformer models. But here's the thing, it did it while being significantly faster and using less memory. That's a big deal.
Huge, especially when you think about how resource-intensive those transformers can be. So, what does this mean practically? Can you paint a picture for our listeners?
Imagine a world where analyzing those huge volumes of text, legal documents, medical records, those massive scientific papers becomes super fast and efficient. That could revolutionize research, legal work, any field that deals with tons of information.
Okay, I'm starting to see the potential here. But before we get too carried away, I remember the paper touched on combining FNet with those traditional attention mechanisms. What's the story with these FNet hybrids?
Right, they didn't just stop at FNet. They wondered, what if we took the best of both worlds? So they created these hybrid models, combining a few layers of good old-fashioned attention alongside those Fourier transform layers.
So kind of like adding a fine-tuning knob to FNet, giving it that ability to zoom in on specific details when it needs to.
A good way to think about it. And guess what? These hybrids actually achieved near BERT-level accuracy, all while still enjoying that speed advantage. Like, maybe we don't need attention in every single layer to get great results.
Food for thought for all those NLP researchers out there. This whole hybrid idea, it reminds me of another concept, knowledge distillation. Could that play a role here too?
You're on the right track. Knowledge distillation is like, imagine you have this brilliant professor, incredibly knowledgeable, but their lectures are super long and dense.
Yeah, like trying to drink from a fire hose of information.
Exactly. So what you do is you get that professor to teach a younger, more agile student who can then relay those key insights in a more concise, digestible way.
So in the NLP world, you'd have a big, complex transformer model teach a smaller, more efficient FNet model, sort of passing on the torch of knowledge.
Precisely. And that could open up a whole new world of applications. We could run these powerful language models on devices with limited resources. Imagine your smartphone or even those tiny Internet of Things devices understanding and responding to complex requests in real time.
The potential is mind-blowing. Okay, shifting gears a bit here. We've talked a lot about the Fourier transform, but I noticed they experimented with other transforms too, like Hadamard and Hartley. Did those perform as well?
Interestingly, the Hartley transform actually performed just as well as the Fourier transform. It makes you wonder if there are other simple math operations out there that could be just as effective. It's like this paper has opened up a whole new toolbox for NLP research.
It's challenging the assumptions, right? Making us rethink what's really necessary for effective language processing. But where do we go from here? Is FNet a paradigm shift, or is it more of a stepping stone to something even bigger?
I think that's the beauty of research like this. It sparks more questions than it answers. It pushes the boundaries of what we know, and that's always a good thing. It's exciting to think about where this could lead.
It definitely leaves us with a lot to ponder. So for our listener who's been following along, maybe not a deep learning expert, but definitely intrigued by all of this, what's the one key message they should take away from our discussion on FNet?
I'd say it's this. Simplicity can be surprisingly powerful. FNet shows us that you don't always need the most complex, resource-heavy methods to achieve impressive results. Sometimes it's about finding that elegant solution, that shortcut through the complexity that leads to new insights.
It's about looking for that elegant solution, like you said, that clever path through the forest that gets you where you need to go, but maybe with a little more grace and efficiency.
Exactly. And who knows what other hidden gems are waiting to be discovered. There's a whole world of possibilities out there in the world of mathematics just waiting to be applied to NLP. It's a field that's ripe for innovation, and maybe, just maybe, someone listening to this deep dive will be inspired to take the plunge and explore these ideas further.
And if you're feeling that spark of inspiration, we absolutely encourage you to check out the original paper, FNet, Mixing Tokens with Fourier Transforms by James Lee Thorpe, Joshua Ainsley, Ilya Eckstein, and Santiago Antagnon. We'll be sure to include a link in the show notes. Don't be intimidated by the technical language. These researchers did a great job of presenting their findings in a way that's accessible, even if you don't have a deep background in all things deep learning.
It's a fascinating read, and who knows, maybe you'll be the one presenting your own groundbreaking research at a future AI conference. Stranger things have happened.
That wraps up our deep dive into the world of FNet. We hope you enjoyed the journey with us.
It's been a pleasure exploring these cutting-edge ideas with you and our listeners.
To everyone tuning in, keep that curiosity alive, keep those minds exploring. You never know what amazing discoveries you might make.
And remember, keep asking those big questions and keep diving deep into the world of knowledge.
Until next time, we'll see you in the next deep dive.
It really makes you wonder what other mathematical tools are out there just waiting to be applied to NLP. There could be a whole treasure trove of elegant solutions hiding in plain sight.
That's what's so exciting about research. It's all about pushing those boundaries, right? Exploring those uncharted territories. And who knows, maybe someone listening to this is getting that spark of inspiration to dive into this field and make their own discoveries.
I love that thought. Imagine someone listening to this gets hooked on FNet, starts experimenting, and ends up presenting their own groundbreaking research at a conference.
It happens. NLP is definitely a field with so much potential for new ideas, new approaches. And for anyone who's feeling that pull, I say dive in. Check out the paper we've been discussing and see where it takes you. Absolutely. For anyone who wants to explore further, the paper is FNet, Mixing Tokens with Fourier Transforms by James Lee Thorpe, Joshua Ainsley, Ilya Eckstein, and Santiago Antagnon. We'll make sure there's a link in the show notes.
And don't worry if you're not a hardcore deep learning expert, the authors did a great job explaining things clearly. You don't need a PhD to get the gist of it.
Well, that brings us to the end of our deep dive into FNet. We hope you enjoyed the journey.
It's been a pleasure, as always, exploring these cutting-edge ideas with you and our listeners.
And to everyone tuning in, keep those brains buzzing, keep that curiosity alive. You never know what breakthroughs are waiting around the corner.
Absolutely. Never stop asking those big questions and keep diving deep into the world of knowledge.
We'll see you in the next deep dive.